Yes, I'm very happy to be here. This is actually the first time for me to speaking to an audience of your caliber. So I don't often speak to an AutoML audience, so to speak. I speak to an NLP audience. That's been the background of my research for the past 10 years now. So I am a natural language processing person. And in general, I probably might have some ideas here to share with you. I've kind of like brought these ideas to the table to kind of like maybe have a discussion with you. And so I'm totally open to you disagreeing with some of these ideas, right? Because I know you're traditional like optimization people, like dealing with numbers and things like that. And there's a lot of debate in the natural language processing field, especially dealing with like NLP these days in terms of like how well do large language models actually understand numbers, right? And how well can they solve for like automated machine learning problems as you know them. So I'm like really open to discussing some of these challenges and issues that you see around some of the topics that I'm going to discuss with you today. In fact, I am super interested to learn about them because I think that they could be like potentially really interesting research topics that we could like, or you know, that one could pursue as like master thesis objectives or PhD thesis objectives and so on. So kind of to just discuss like what I'm going to talk about, I've kind of brought to the table some notable benchmark data sets around the topic of scientific experimentation and how LLMs have been like applied in these contexts, which is to say that I am going to talk about these broader benchmark data sets, but then it's kind of like also open to you because I will share the slides later, so it's also open to like a very diverse community to put these ideas to the test, because some of these problems have been identified as challenging problems in the field indeed. So with that, let's get started. So the title for my talk is Large Language Model Assisted Scientific Experimentation and Overview. And with this, I should, of course, state a disclaimer is, you know, this talk is not going to be a comprehensive overview on the field. It's pretty vast and it's constantly evolving. So every next day you see like a new finding released on this topic. So I do not claim to present like a comprehensive overview on this topic. Nevertheless, I've kind of identified 5 benchmark data sets, or at least 5 notable works in this field that have at least at some point contributed to like moving the needle on this topic of scientific experimentation. So with that, let's begin. So to set the stage, so first of all, let's motivate AI assistant for scientific experimentation, right? So why do we need AI assistants for scientific experimentation? Aside from the obvious, you know, concern that we want to save the time for researchers to possibly build solutions in like minutes as opposed to like days or years and so on. So that's kind of like the goal, like the golden objective that we are going for. Nevertheless, so kind of like to practically like ground or motivate why we need AI assistance for scientific experimentation, we recognize that the complexity and expertise for successful ML machine learning experimentation pose significant barriers to entry. So this is kind of like one of the challenges that we identify. So this has kind of like driven research interest in the possibility of automating aspects of the machine learning workflow. And this is something that you've heard about in the past few days. So that's neural architecture search, AutoML, so figuring out like, you know, the optimal configurations for your machine learning problems. So, so kind of now, the second aspect being The emergence of advanced language models, large language models, or generative AI technology with the ability to understand and generate human-like text. So this presents a promising opportunity to further automate machine learning experimentation end-to-end. Much of this is up to debate so far, but we are kind of like at the very early stages of exploring generative AI technology to, help automate machine learning experimentation end-to-end. So this is kind of like a new application area. So the overarching theme for my talk today, and I've prepared this as a sort of a presentation, so I don't have demos, so to speak. Nevertheless, I am kind of pointing to some resources in the field that you could, like after the talk, download and try out for yourselves. So my hope is to kind of like introduce these paradigms and discuss these data sets, and then you can like go away with some like concrete application areas perhaps that you could try out for yourselves. So, so with that, the overarching like question for my talk is, or this area of like scientific experimentation broadly is, can we develop an AI agent or an autonomous agent or an autonomous generative AI application that is capable of conducting machine learning experimentation autonomously? So that's kind of like the broad idea that I just want to throw out there, right? So let's move on. So now I kind of want to point to the survey paper that I have been involved in very recently. The title of the survey paper is called Transforming Science with Large Language Models, a survey on AI-assisted scientific discovery, experimentation, content generation, and evaluation. So basically, in this paper, we kind of like try to discuss the existing notable works around various areas of the application of large language models within scientific workflows. So not just experimentation, but just in the broader area of scientific workflows. So at the moment, this paper is in review. However, we have published a preprint on arXiv. So why am I talking about this? This is kind of like part of, so I've based part of my talk on the survey paper. That's kind of like the methodology that we adopted in our survey. So we looked for AI support for individual topics and tasks. So we are kind of looking at how LLMs support science, and especially like different aspects of the scientific workflows. So we have looked at literature search, summarization, and comparison. So that's one area where generative AI is applied. Another area is AI-driven scientific discovery. So this is like generating creative ideas, generating hypotheses in science, and also in experimentation. A third aspect that we've looked at is text-based content generation. So this is like literally generating like parts of a paper, so to speak, based on evidence. A fourth part that we've examined is also multi-model content generation and understanding, and finally peer review. But for the purposes of this talk, I'm just going to focus on one aspect, which is automated experimentation. So this is kind of like the aspect that I'm going to zoom into this talk, just to make it relevant for the automated machine learning audience that's here. So with that, we can get started. So this is the section of the paper, or the conceptual figure that we had in the paper to the section of scientific discovery that dealt with idea generation, hypothesis generation, automated experimentation. And so as I mentioned before, I will just focus on automated experimentation. So we kind of like blank out the remaining aspects. So when we talk about an experiment, what is an experimental setup typically, right? So there's like, we kind of formulated this or tried to generalize this in terms of like four parts. So first of all, we specify a task that needs to be solved. So in this case, you basically see, okay, I'm going to read this out. So that's train a multitask model on ClinTox to predict toxicity and FDA approval. So this is basically a data set of like drugs. So they're basically like chemical formula, and you kind of want to predict, you know, the toxicity of this drug, and you also want to predict whether the FDA is going to approve it or not. So these kinds of things. So that's the task. So you specify the task in advance. Then you have some raw data. You have some data that backs up your task, right? So this is what you use to like define your problem on. This is what you use to define your machine learning objective on. Then you pick some methods to solve your problem. So that's the next part of the third part of this problem. And finally, you have, you know, your expected output. So your expected output could literally be a program that solves the problem, or it could be the output that you want to get. So this could be a table of data. So it's kind of like, it depends on the kinds of modalities that you've dealt with. So this output could really be quite specific to the problem that you're handling. So that's kind of like how we approached at least the review of this one small sub-aspect in this paper. So with that, having said that, the plan for my talk is to visit two main aspects around experimentation and leveraging large language models for scientific experimentation. So the first part of my talk will visit three different paradigms that, or three different research works or benchmarks that have been introduced for scientific data discovery, data-driven discovery automation. The second part of my talk will kind of like is closer to the heart of this summer school. So it will look at language models that have been applied for automated machine learning and how they have been applied for automated machine learning. So let's get started with the first part. So scientific data-driven discovery automation. So that's kind of a mouthful. So in this context, the first benchmark that I want to talk about is called Science Agent Bench. So this was a work that was published in 2024, so it's fairly recent. Basically what Science Agent Bench does is that it introduces scientific data-driven discovery. So it kind of formulates this task as a programmatic task, right? So how is the experimental task handled here? It's basically a programming task, so it's a coding task. The idea here is that language agents serve as science co-pilots that can write code to process, analyze, and visualize data. So this is not just one function that it's attempting various kinds of functions around data analysis. And it's trying to automate these workflows around it, or it's at least trying to create benchmarking like points or data instances that one can use to test whether they're able to solve for certain scenarios. And this is quite analogous to software development co-pilots. So the task formulation in essence, is basically a code generation problem. So the view taken here about scientific data discovery automation is programming. So it's like writing code to basically read some data and solve for that data as an output. So the output is easily verifiable and it's directly usable by a scientist without additional modification efforts. Now what's interesting about this data set is that the tasks that have been defined in this benchmark have been sourced from 44 publications. So they actually come from papers that have been published. So they are actually testing for real problems. And from these papers, they've identified 102 tasks because they've broken down some of the aspects of the task into like individual problem scenarios that can be solved potentially by large language models in the long run. So this is kind of like a view of, like a conceptual view of Science Agent Bench. So this is a figure taken from the original paper. So on the top of the screen, you basically see the various kinds of objectives that have been encoded within Science Agent Bench. So they are categorized into 4 main types. So the first type is data processing. So this benchmarking data set is interested in identifying like solutions for feature engineering, feature selection, data selection, and so on. The numbers in the parentheses correspond to the data instances precisely addressing that aspect. The next aspect is model development. And this is kind of like, I think, closer to the nature of the AutoML summer school, right? So it's kind of like writing programs, like full-fledged programs that can do deep learning or machine learning. It depends. The third part of the objectives that are addressed in this benchmark is data analysis. So this involves statistical analysis or geospatial analysis or computational analysis. And the fourth part is visualization. So kind of creating plots over like the input data that you have. So the kinds of plots that they deal with is map visualization because they have a focus on geographic data, but also molecule visualization because they have a focus on biochemistry data. So in terms of the tasks that have been like published within Science Agent Bench, and indeed Science Agent Bench is a publicly available resource. You can download it and test it out for your own, for your own purposes, especially if you want to focus in on one of these problems, one or more of these problems. So that's kind of like leaning into the which question. So which types of coding tasks have been defined in Science Agent Bench? And that's kind of like the first part of this figure that I've kind of like talked about. The second part of this figure kind of shows you a visualization of the types of input data sets that are in Science Agent Bench. So so for example, the first figure here, so figure A, is a cell image in bioinformatics. So that's kind of like one of the data types that you would find within Science Agent Bench. The second figure here is molecular activity visualization in computational chemistry. So this kind of already tells you that we are switching to a different discipline here and a task in a different discipline. The third figure here is a flooding risk map in geographical information science. So this is kind of like a geo problem. And the fourth image is an EEG time series in psychology and cognitive neuroscience. So now these 4 figures are actually exemplary of the 4 disciplines that are encoded within Science Agent Bench. These are, of course, visualizations of the data sets, but the data sets are available in various formats, so that's like tabular format and so on and so forth. So what is the motivation for this work? Or if we kind of like wanted to reflect about like why, this work was created, so like what motivated the authors to create Science Agent Bench? So this is a quote from the paper directly. So in this work, we contend that for a language agent to fully automate data-driven discovery, it must be able to complete all essential tasks in the workflow. This includes model development, data analysis, and visualization. That's why Science Agent Bench has like these different aspects encoded into it. So thus, we advocate careful evaluations of the agent's performance on these tasks before claiming they can automate data-driven discovery end-to-end. So that kind of like leans into the complexity or the complex nature of this problem. So scientific discovery end-to-end is a very complex problem. And what these researchers have done who introduced Science Agent Bench is kind of like broken down this problem into like smaller parts and kind of said, okay, how do generative AI technology address these subcomponents? So as an example task formulation, we can take a look at another figure from the paper. So, so this figure basically is organized into 4 parts. So let's take a look at each part. The first one is the task instruction. So at the outset, I basically want to say we are kind of using large language models to address these problems. So in order to use large language models to address these problems, we need to prompt them in a certain way. And all of these task formulations that I'm going to talk about is like these prompting methods that these researchers have used to solve for like the tasks that they have in their benchmark. So they've kind of like organized their task into like specific subsections. So the first part of the prompt would be the task instruction. So that's kind of like what you see highlighted on the screen in this green box. So the task instruction describes the goal of a task in data-driven discovery and its output requirements. So the task formulation that we have on the screen is from the computational chemistry domain. And the type of machine learning objective that it addresses is deep learning task type. So if I could just read it out, it's the task that we saw a few slides earlier. So that's train a multimodal model, a multitask model on the ClinTox data set to predict a drug's toxicity and FDA approval status and blah, blah, blah. So that's kind of like the task as it's been introduced into the prompt for the large language model. So just to kind of like give an idea as to how different these task instructions might be given the different kinds of disciplines that Science Agent Bench addresses. Another example here on this slide is from the bioinformatics domain. And here the task instruction basically says, train a visualization model on the given data and perform a 1 versus all differential expression test for each cell type, extract top markers for each cell type using the results, visualize them as a dot plot with the cell types organized using a dendrogram, and so on. So the objective addressed by this task instruction is a data visualization task type. So that's kind of like what this instruction is going for. Another example from the data set is from the geoinformation science domain. And this kind of like asks or is an instruction to prompt the LLM to analyze and visualize elk movements in the given data set. So the given data set would be a tabular data set, for instance, or a tabular historical data sets of elk movements in this given region. And so the instruction is estimate home ranges and assess habitat preferences using spatial analysis techniques and so on. Again, this is a map visualization task type. So this is, a third example. So this gives you an idea of like the different kinds of tasks encoded within Science Agent Bench. So the next part of this instruction is the next part of the prompt, or the prompt contains also some information about the data set. And how is this information fed to the large language model? So that's fed in terms of the data set's directory structure and a preview of its content. So when we see later the kinds of experiments that have been done with Science Agent Bench have been done in scenarios where agents have file navigation tools or agents do not have file navigation tools. So in the situation where agents do not have file navigation tools, such information is actually helpful to the LLM to figure out how to correctly use the data set. And in the case where the agents have the capability to navigate file systems, it helps them to save a few turns of the interaction. So it kind of is like a skip of a few steps because it already gets the data directly structured in advance. So another aspect of the task formulation or the prompt specification to the generative AI model is the expert provided knowledge. So this is kind of like additional optional knowledge that is provided in addition to much of the task specification that has been given to the LLM. And oftentimes this is necessary because it helps disambiguate or contextualize some terminological jargon that is quite prevalent within science. So expert provided knowledge can include explanations for scientific terms, formulas to conduct analysis, and example usages of programming tools. And within this particular benchmark, they have been human annotated. So this is like gold standard signals that have been added into this data set. In fact, they have been provided by subject matter experts. So I mentioned earlier that there's like 4 different disciplines represented within Science Agent Bench. So the researchers in this work contacted, senior PhD students or professors within this specific disciplines to annotate like the data that went into like the expert provided knowledge or the context. And the annotation process was as follows. So they kind of like at the beginning, they said, okay, we have these bunch of publications and we identify these tasks from these publications. So now we need a human to actually look at these tasks and, actually verify that they can actually be realized as machine learning tasks or realized as realistic, like generative AI objectives. So the first question that they pose to the human annotators is the annotated task a realistic task? So that's kind of like one of the first questions. The second one is, does the task instruction give an accurate high-level description of the program and uses professional language of all disciplines? So they're kind of looking carefully at part A here and kind of like providing like additional signals that are necessary, that they think are necessary to define the problem. And the third part kind of like feeds into this expert provided knowledge. So the domain experts who were involved in this exercise were requested to provide up to 3 pieces of knowledge that might be needed for solving the task. And finally, they had to revise the rubrics for grading the program, but we'll see that much later. Okay, so the fourth part of this formulation you see here is the annotated program itself. So this is kind of like the gold standard program that is expected from the generative AI, right? From the generative AI tool. So that's kind of like how well does it solve for this given task instruction that's provided to it. So this annotated program was basically like the gold standard that was used to evaluate the program that was generated by the LLM. So where did this annotated program come from? So that's adapted from an open source code repository which accompanied the scientific paper. So the validation, so it kind of like served as the validation data in this context. So now looking at the evaluation and how Science Agent Bench was, so some of the results that were released with this benchmarking data set. So the researchers involved in this work kind of tested some open weight large language models. So they tested Llama 3.1, which was probably the state of the art at the time. And this field is moving so fast, so you kind of like see new LLMs released every day. Nevertheless, I think this was the state of the art at the time of writing of this paper. And some of these are relatively large language models. So that's like 405 billion parameters and 123 billion parameters. So these like really large models are known to have like sophisticated processing abilities, but we can see how they do with these scientific processing tasks eventually. They also tested some proprietary large language models. So proprietary large language models are those that you pay for, right, to get access. So they tested GPT-4o and Cloud 3.5 Sonnet. So that was already released at the time. And they tested 3 different agent frameworks. So the first one is not necessarily an agent framework, so to speak. So they actually just directly prompted the LLM. So it's like a simple framework that doesn't interact with any programming environment. At the end, what is an agent? It's almost like a function, a complex function that you define which can run autonomously to perform a certain task. So in that respect, they kind of like define these functions, yes, but they kind of directly prompted the LLMs to perform the task. So the second framework they tried is Open Hands Code Act. So this is known as a generalist agent development framework especially for code generation and software engineering. So this provides 3 kinds of tools in the environment and defines different actions for an agent to interact with these tools. So the tools are a Python code interpreter, a bash shell, and a web browser. So basically, if you define these functions within this environment, so it can be called within like this environment. And so the third agent framework is self-debug. So this is a code generation framework for large language models to execute their generated programs, access execution results, and then reflect onto the results to improve each program iteratively. So it offers an additional reflection capacity over like the results of like a previous execution. So that's how these kind of frameworks differ from each other. And they evaluated the task with respect to 4 metrics. So the first metric is the valid execution rate. So this is basically testing whether the program can execute without errors and saving its output with the correct file name. Then the success rate. So this is kind of like looking at the output of the program and identifying whether it meets success criteria for each task goal. So this could be the test set performance, or the prediction answer matches, or in the case of visualization tasks, the quality of the visual output that was produced. And the way this was implemented is via separate programs. So they kind of like implemented different kinds of evaluation programs to measure for each of these fine-grained criteria. They also had something like the CodeBird score, which is kind of matching how similar the generated program resembles, the annotated program, so the validation program. And finally, the API cost. So this was kind of like identifying how much the experiment cost in one task. So that's a results table from Science Agent Bench. So the first insight that they had to share from their experiments was that execution feedback is necessary for large language models to generate useful programs. So this is where we compare the direct prompting scenario with the self-debug scenario. So in the direct prompting scenario, the generative AI tool kind of like produces this code to like, solve for that task. However, that code is not able to be executed within the environment that it's generated in, right? So there is no feedback that can be gone into the LLM that says, okay, this code worked well or it didn't work well. However, in the self-debug agentic framework, the code could actually be executed within that environment. And that was fed as feedback as a reflection feedback to the agent, so that it could then iterate over like the previously generated output. So that's basically what Insight 1 is pointing to. Execution feedback is necessary for large language models to generate useful programs. So without executing its code in the direct prompting scenario, among all the experiments, Cloud 3.5 Sonnet was seen to be like performing the best. So basically, it could execute 17.7% of the tasks independently. So this is quite a low percentage. Nevertheless, it's like, you know, very early works into like conducting scientific experimentation end to end. So without executing code, Cloud could, could perform 17.7% of the tasks independently without domain expert knowledge, and with domain expert knowledge, it was slightly better, so 21.6%. On the other hand, self-debug, which actually got the feedback of like the execution of the generative AI output from a previous stage, nearly doubled the success rate. So it kind of like was at 32.4% independently. So this kind of like offers some insights into like what actually helps to improve, you know, LLM behavior, generative AI behavior to solve for these tasks. Now, when comparing like the different agentic frameworks that we have here, so there's just two, the Open Hands Code Act and self-debug. The second insight that they shared in this paper was that agent design should consider costs and capabilities of LLMs. So this is to say that the Cloud Sonnet using self-debug, so using self-debug can successfully solve 10.8% more tasks. So it's basically more effective within this particular framework. Furthermore, it costs 17 times less API fees, which is a critical factor to consider for practical applications. So how much of these functionalities are already encoded within the agentic environment? So that kind of really cuts the cost down quite significantly. So the takeaway here is that large language models-based agents do not always benefit from a large action space with complex tools. So this is a bit more open-ended in terms of the actions available to the large language models to solve for the task. So the third insight was that language agents cannot solve complex data-driven discovery tasks yet. And this is something that we've seen before already. So here I kind of like want to highlight the keyword that's complex data-driven discovery tasks. And how is this measured in this paper? So that's kind of like what is shown on the figure on the left. So here we kind of like measure complexity in terms of lines of code. So the authors looked at the number of lines of code in the goal program. And what you see on the y-axis is the number of successful runs versus the number of unsuccessful runs. So 0 corresponds to the number of unsuccessful runs and 1 corresponds to the number of successful runs. As you can see, majority of the successful runs are leaning towards the programs that are relatively shorter. So they're not very, complex in terms of like the program execution. In terms of lines of code. So more than 75% of succeeded tasks lean to the simpler side because their goal programs have less than 58.6 lines. So that's kind of like an average number. The second way they measure complexity or complex data-driven tasks is by looking at different disciplines and the subtask categories. So that is kind of like shown on the figure on the right side of the screen. So that shows you the task error rates. And this is with respect to the different disciplines. And the legend here shows you the aspect of the task addressed. So data processing tasks, model development tasks, data analysis tasks, information visualization tasks. So you kind of see like where the large language models have very high error rates in this context. So, and it also gives you kind of like an ablation analysis as to which disciplines the large language models are actually finding difficult to solve for in this generative AI manner. So that's the third insight. The fourth insight is that some LLM-generated programs are close to success but hindered by some bottlenecks, such as data loading and processing. So note that the tasks in Science Agent Bench kind of like address like the end-to-end program generation. So it's like from the beginning, you're provided an input data set, and at the end, you need to produce this program that kind of like solves for that data set. So they also did an ablation study as to in which parts of that program generation are the large language models failing. Data loading, data processing, modeling or visualization, output formatting, output saving overall. So this kind of like points to saying that future research may, for example, improve language agents' capability to better process scientific data and focus on like specific aspects within the program that are actually not capable of being handled by the large language models or the generative AI agents, and figure out alternative strategies to kind of solve for them, maybe heuristic-based methods or something like that. So in summary, this model using self-debug so Cloud Sonnet, this was in 2024, maybe it's different now, given some of the more advanced coding models that have been released. Using self-debug can successfully solve 10.8% more tasks than Open Hands Code Act while costing 17 times less API fees. So it's always like a consideration that we make when using these proprietary models. Like, is it effective both in terms of time, but also in terms of cost to solving these experimental tasks than a human solving these problems? So basically, this leans into saying that agent design should jointly consider costs and performance to maximize their practical utility. And it was seen within Science Agent Bench, which also proves that it's quite a challenging data set and still is open to solve for as a resource. So within the experiments published in the paper, the best agent could solve for only 32.4% of the tasks independently, and 34.3% of them with expert provided knowledge. So there is a lot of room for improvement in terms of like applying generative AI models to these tasks. So the takeaways here with Science Agent Bench would be that language agents hold significant potential in augmenting human scientist productivity, because it was noted, like in this paper, when they had the human annotators annotate each task, it took a trained annotator at least 2.5 or 3 hours on average to even adapt an existing program from public sources, and potentially much longer for the subject matter expert to write a program from scratch. So in contrast, the language agent could usually do it within 10 minutes. And this is common knowledge, right? We all know it. But this is kind of also to say that with the benchmarking efforts that were introduced in this paper, the language agents were not so effective in solving for these problems. So while they took lesser time to produce a solution, the solutions weren't solutions that you could actually readily use in your workflows. So Science Agent Bench serves as a benchmark for rigorously measuring progress toward developing language agents to assist scientists in data-driven scientific discovery. So that's one benchmark data set. The second benchmark data set that I want to talk about is called SciCode. So this is also within the same paradigm of scientific data-driven discovery automation. So this was also published in a research paper that was in the NeurIPS conference in 2024. So what SciCode does is also address the scientific data discovery automation as a programming task, but they kind of break down the task in terms of like function coding. So it's like divide the task into sub-problems and get the generative AI model to address these sub-problems and then combine the sub-problems into a long program. So this is how SciCode differs from SciAgent Bench, where SciAgent Bench expected the agentic framework to kind of like generate the whole program. What SciCode was addressing was like sub-problems that could then be combined to form the whole program. So the task formulation was kind of similar to SciAgent Bench. So they identified a main problem. However, here's where it differed. They decomposed the main problem into sub-problems that could be addressed programmatically. So the LLM could be expected to write functions for the sub-problem. So this is a different take on SciAgent Bench. So furthermore, within SciCode, so the two works kind of came out, in similar timelines. So it's kind of like these ideas are published within different research groups that are not, fully because this is a new topic. So it's almost like a hot topic that's, being kind of addressed by different research groups. So different people publish at different times. So that was the way these researchers approached this problem. So within SciCode, the experiments were performed in a direct prompting setting. So this is also how the experimental settings within the SciCode paper differs from SciAgent Bench, because in SciAgent Bench, they actually use some agentic frameworks and environments. So in SciCode, they were actually doing, direct prompting. So there was no agentic framework tested like self-debug, where external tools are called to execute programs that offer feedback to the LLMs. But this doesn't take away from the benchmark data set that the researchers who introduced SciCode, offer. So that benchmark data set still has its own potential or capacity to be explored for solutions and so on. Nevertheless, the experiments that were performed in this paper kind of just use the direct prompting setting to relate it to SciAgent Bench. Now, SciCode actually presents as a highly multidisciplinary data set of coding problems. So this is also another aspect as to how it differs from SciAgent Bench, is in its disciplinary coverage of coding problems associated with research questions. So what you see on the screen are the 4 disciplines that were covered in SciAgent Bench. And now you see SciCode, which is a lot more fine-grained. So it has 16 different fields in science. The top-level fields being, and these are the natural sciences, right? So mathematics, physics, chemistry, biology, material science. And within it, the 16 fields, so the subfields, so numerical linear algebra, condensed matter physics. And within the parentheses, you see the problems that were identified for each of these disciplines. So this is to say that if you download this data set, you could actually choose to focus on, some of these sub-problems that they have, depending on your interests, of course. So again, they kind of address experimentation as a programming problem. So that's their take on experimentation. And the kinds of problems that they address here are numerical methods. So they are more advanced than we saw earlier in the SciAgent Bench dataset. Simulation of systems, scientific calculation. So scientific calculation meaning tasks to perform transformations based on scientific formulas to get physical observable of interest instead of raw experimental data. And what's a great selling point of SciCode is that they have some notable research problems within this benchmarking data set, which actually have been parts of problems that were, part of the Nobel Prize at a certain year and so on. And the slide kind of lists some of them. So this is also a very interesting part of this data set, to kind of solve for these sub-problems that were part of these very challenging problems seen in a particular field at a particular point of time. So you see chemistry, physics, a lot of emphasis on physics, Nobel Prize problems. And I'm actually going to pick on this example because this is also the example that the authors kind of like expounded in their research paper. So this is the Haldane model for the anonymous quantum Hall effect. So I am not a physicist, so I do not know this problem. I'm just a natural language processing person. So for me, this is kind of like a black box, right? Nevertheless, it's interesting to see how these computer scientists decompose this problem, or at least an aspect of this problem, and defined it as a programming task. So what was the problem that they kind of like defined in this context? So first of all, they have a main problem, and then, like I mentioned earlier, Psycode decomposes a main problem into subproblems and then expects the generative AI model to solve for these subproblems and then combines them together as one solution, right? So the main problem here was that they wanted to generate an array of some numbers for the model on a hexagonal lattice by sweeping the following parameters. So to kind of read from the caption here, so they kind of use, how do they specify, the parameters of the problem themselves? So they use this docstring format to specify the parameters of this problem. So this is also very important to consider in terms of like canonicalization. So this is where you normalize a representation so that the LLM sees this consistent representation of a certain problem, like across different runs of the LLM. So this is also important in the context of large language models. So in general, within Psycode, each problem includes a scientific background when needed. So this should be each subproblem. So that's now kind of looking at the subproblems that this main problem was decomposed into. So this is very similar, or some of the ideas are kind of shared between SciAgent Bench and Psycode. So each problem has a scientific background when needed and detailed instructions provided in this specific format. So this is where it differs in the format that it adopts to define the problem, or the instructions for the problem or the subproblem. And solving requires implementing multiple Python functions for subproblems, then integrating them into a complete solution. And indeed, in this benchmark dataset, the gold standard solutions and multiple test cases were provided for all the problems, enabling reliable automatic evaluation. So this is also quite interesting to kind of take a look at in terms of like which Python libraries were used by the problems in Psycode. So that's kind of like a distribution of the Python libraries that Psycode, or the problems in Psycode, kind of like relied on. So NumPy, SciPy, iterative tools, math, and so on. So they also performed experiments on this benchmark dataset that they released, and that's kind of similar to SciAgent Bench. So they tested when, the scientific background context was provided or not. So here they were actually testing for the model's intrinsic scientific knowledge when it was tested without the scientific background. So they also tested for, so this was essentially a pipeline, right? So they kind of like tested for including in the context the previous generated solutions or the goal solutions to previous subproblems. So they kind of like fed it into the context, and then they see how it impacts the model's performance on like predicting the next function. So that was another ablation setting that they addressed. They also looked at main versus subproblem levels. So subproblem levels is actually looking at like individual subproblems that the generative AI model generated, or the combination. So after you combine the subproblems, like was it executing and solving for the main problem? So that was the level they tested for. And finally, okay, then how many LLMs did they test, or how extensive was the benchmarking, right? So they tested proprietary LLMs versus open weights LLMs. And here we can see like this was around the same time perhaps of like the SciAgent bench work, because they also were able to test Cloud 3.5 Sonnet. So that was a model released around that time. And in terms of metrics, they used the pass at one rate, which is how often is the model correct. So they defined certain test cases for the subproblems that were included within their benchmarking data set. So they want to test how often the model was correct, or how often the model generated the code that was correct or passed the test cases on the first try. So this is an overview of the results on this particular benchmark data set. So now you see a range of performances. So this is like aggregated in terms of like the proprietary models in the top part of this table, and then the open models in the bottom part of this table. So when we look at the subproblem pass at one rate, we see it ranges from 14.6 to 26.0. So again, Cloud 3.5 Sonnet is proving to be quite effective. But quite effective is a very relative term, but it's surpassing the other models, I should say. So it's like performing at 26.0. So again, it's quite a challenging benchmark and is an open problem to solve for. And in terms of the main problem, the pass rate is even significantly lower. So it's from 0.0 to 4.6%. So a lot of the open models are not able to even solve for like any of the problems that are introduced in this benchmark data set. So in summary, like tying into SciAgent Bench or Science Agent Bench, Cloud 3.5 Sonnet was most effective, but still at a very low pass rate. So that was 4.6% of the main problems. And there's other insights, of course. So this data set, I guess the takeaway insight from this work is that they introduced a highly multidisciplinary data set, and it presents as a challenging benchmark. So it's quite nice to like try it out for oneself and see how you might solve for any of these disciplines as well. So now the next work that I wanted to talk about is ML Agent Bench. So this is again another benchmarking data set in the same paradigm of scientific data-driven discovery via like coding problems. So this was a paper that was released in, on arXiv, at least in 2023. So the motivation is quite similar to Science Agent Bench. Nevertheless, now it starts focusing on machine learning problems. So it's highlighting problems as machine learning problems. And these problems, of course, can come from different disciplines. So it's now not focusing on differentiating the disciplines, but it's actually focusing on identifying if they are actually machine learning problems. So the motivation for this work was a central aspect of machine learning research is experimentation. The process of designing and running experiments, analyzing the results, and iterating towards some positive outcome, example, improved, evaluation metric, and so on. So the central question that they asked is, like, could agents driven by powerful language models perform machine learning experimentation effectively? So this is very close to much of the two works that I've talked about before, right? So what are the types of tasks that they address? So they just categorize them as one type, machine learning tasks. And the examples here are, so this is the kind of instances of the data that are present in this benchmark, right? So that's the CIFAR 10 data set. So I believe this is an image processing data set. So you classify images as types. So I think there's like 10 classes of images, the last I checked. So that was, you classify an image as a type of a person or this kind of a thing. So they introduced that. They have these examples within this benchmark data set. But they also included some Kaggle challenges that were launched between 2022 and 2023. So these are all human curated like sets of data that were included in the ML agent bench. So they kind of like selectively identified machine learning problems. And so of course I'm talking about, scientific experimentation. And the two works that I talked about before kind of leaned into saying, okay, there were publications, and these publications like produced these like source code that accompanied the papers or released these research problems and so on. But ML Agent Bench kind of like goes more into the community, and it kind of like tries to identify what machine learning problems are being addressed in the community. So this figure basically encapsulates how they define the task within ML Agent Bench, or how they address the task. So what is the task formulation? So that's basically reflected in the first part, or the top part of this figure. So each task is specified by a task description. Again, note that large language models are part of this like scenario, right? So we are always trying to formulate a prompt to basically trigger the large language model to be able to satisfy this task or perform this task. So what ML Agent Bench, of course, shares with the other two benchmarking data set is all of them have a task description. So you're specifying what task needs to be performed. Now, you might also note that this set of starter files is also common with one of the benchmarks that we've seen earlier, which also specified the working directory. So this was kind of like an input information that was given to the agent. And a third part is the evaluator. So they also provide the evaluation metric that's expected from the task. And of course, like all of these agents are then instantiated in an environment. And the environment in this case was defined with a specific set of actions and states. Nevertheless, to look a little bit closer at the starter files, so what did the starter file include, or what did this specification include? It includes the training and the testing data. It includes data descriptions, metric descriptions, and the starter code. An interesting thing to note here again from that connects it to the previous work is that some of the starter code relied on diverse machine learning frameworks. So that's like PyTorch, TensorFlow, Keras, and so on and so forth. So this is now going deeper a little bit into machine learning problems, right? So, and another aspect to notice is, how is this a problem to solve for? So the starter code was oftentimes a baseline implementation. So it wasn't like an advanced implementation of a solution that, crossed the expected accuracy and so on. So it was like the most simplest system that could be implemented to solve for the task. So that was sometimes available as input to the generative AI models, and at other times, the generative AI model in this case had to just generate the code from scratch without even seeing any baseline implementation. So how was this agent environment defined? So the agent was operating over a series of time steps. So these are all unique formulations of like how agentic environments or agentic applications are like defined to solve for, scientific data-driven tasks. So in this case, what they did was they defined each time step into the following parts, so acts. So the agent basically has a memory component, it has a workspace, and it produces a rationale and an action. So the fact that it produces a rationale means that it's already interacting with the large language model. Then the agent is also able to execute, so it can execute an action on its workspace to produce an updated workspace and return observations. Furthermore, it can update, so basically it can update its own memory based on its action and its rationale and observation. So this table basically shows you the kinds of actions that were defined within the experiments that were conducted on ML Agent Bench. So as you can see, some of these actions are rather simplistic. So they're like, read, write, append, copy, edit, so on. So they don't involve large language models. They're just basic instructions to like do a particular function in a Python program. But they also had like 3 manually designed compound actions. So these were kind of like modular. So each of these actions needed to interact with an LLM to complete its execution. So that was understand a file, edit the script segment. And of course, like these are more critical to like, solving for a particular problem that is very different from the baseline, or if a baseline is not given at all. So this slide kind of like shows you what an interaction within ML agent bench looked like, or how they implemented, the agent in action given this benchmarking data set. So they basically had a prompt. The prompt was able to have a historical trace. So it basically knew what actions were executed before. And that was also fed as an aspect of the prompt. And together, this was given to a large language model. So of course, the prompt had like the task description. So some parts of the prompt are like boilerplate, so they don't change at all. The parts of the prompt that change is like the kind of like stuff, like the memory update stuff. So stuff that comes from previous executions and so on. So that's kind of like fed to the LLM, and the LLM is expected to like reason over this data and produce a response, execute an action if necessary, and so on. So in this example, basically what is happening is that the agent starts with a baseline program and is now trying to execute this baseline program. So that's what's happening in this execution action. So they kind of like tested ML agent bench with 7 LLMs. So this was much earlier, so this was in 2023. So now we are seeing some of the earlier large language models as well. And they tested against 3 metrics. So oftentimes also with like LLM research, we are like quite interested in the metrics that we use in evaluating how well these large language models do. And the space is oftentimes like not usually amenable to the traditional quantifiable metrics. So for example, traditionally, if like rouge or bleu worked really well for summarization tasks, they kind of like don't work very well now given large language models, because there are so many different aspects of semantics or reasoning that one needs to think about in terms of like evaluating how well LLMs are doing. So it's kind of like a very wide open space. Nevertheless, coming back to the problem at hand, so ML agent bench. So they tried 3 different metrics. One was the success rate. So this was testing whether the performance metric improved over the baseline in the starter code by at least 10%. So now they're actually like expecting the model to like generate a program or generate a machine learning approach that can improve over the baseline if it existed by at least 10%. And if not, the baseline is 0, and does it like at least improve by 10%. They also measured in terms of like the average amount of improvement of the performance metric and efficiency. So this is basically how fast was the experiment done, given, and also counting for the number of tokens consumed by the agent, because tokens like often add up as like the cost that an agent has. So this table basically summarizes for the results. So on the first column, you see the kinds of data sets that were tested on. So again, we see the CIFR data set like reappearing within this machine learning benchmark. So we see that Cloud version 3 Opus was quite successful at most, at least, well, compared to the other models, it was on average quite successful. So it had a 37.5 success rate. And in fact, it solved for some of the data sets, some of the regression data sets, almost like with 100%, results or success rate. This is another view of the result, which kind of like looks at various aspects that one needs to think about in terms of like generative AI and agents. So how often does the LLM hallucinate? Does the agent always create a good plan of actions? So it's like the sequence of actions that happen one after another, like file edit and execute and so on. So these are all factors that in the end affect like how well this, this environment can operate to solve for like the scientific data-driven discovery. And so an observation made at the time was that GPT-4 was more prone to hallucinations and poor planning compared to Cloud v3 Opus. So that was kind of like what you could see from these bars here. So this is kind of like an example of a good plan versus a bad plan. So on the left side of the screen, you see a good plan. So this is almost like saying, okay, what does an agent do like in a scenario where it's successful? It edits the script, it executes the script, it edits the script, it executes the script. So this is kind of like feedback. Edit, execute, execute. So then it tests whether it's working. A bad plan is where it gets like sidetracked completely. So it like does some stuff that, is kind of unexpected, or it's not logical that it should do. So it like executes a script, then it does understand a file, lists files. So this is kind of something too bizarre and random, and that's when it's like completely derailed. Also in terms of efficiency, we see that, the GPT-4, so on the x-axis you basically see the number of tokens spent. So this is another criteria that folks like look at, is like how many tokens is the agent using to actually complete a task, because tokens equals cost, especially in terms of like the proprietary models. And what is the average success rate? So we want to like have a trade-off between the two, right? So so in this case, GPT-4 Turbo was proven to be like a little bit better, but it kind of like, it's really quite relative what this better means, because Cloud seemed to have spent quite a lot of tokens, but was also more, successful at solving a more amount of tasks. So it kind of really depends on the scenario. So overall, the GPT-4 family improve performance to tokens ratio trend, while cloud models generally improve performance at the cost of more tokens. So this is kind of like what it costs to run, the entire benchmark using GPT-4 Turbo. And that was like, 6 million tokens, $60 with low average success rate of 26%. So this is to say that, again, this is a very early area of investigation, and there's a lot of room for improvement. Nevertheless, I think these benchmarks are quite like solid starting points to begin with to try testing out approaches. So that's the trade-off to always consider to leveraging language models-based agents for experiments, cost versus time. So now I kind of like talked about the first part. Now I kind of want to move closer to the AutoML aspect, which is, how are we doing on time?
Something like 10 minutes.
10 minutes?
How long your second part is? As long as the first part of the
No, it's not as long as the first part. Yeah, I could actually cut it short. So the second part is kind of like some results on like folks having tried language models for AutoML as it's defined in the context of the summer school. So having like this optimal configuration for your machine learning models to solve for certain tasks, right? So I think I'm going to skip this part because this is just case studies, so it's probably not. So I kind of wanted to highlight this work, which is called ML Copilot. So this was introduced by some researchers at Microsoft. So this was basically saying, how to get large language models or how to tap into the reasoning ability of large language models in order to have them, solve for this configuration, like coming up with the optimal configuration to solve for a new task, right? Basically, they wanted to leverage both machine intelligence and human design patterns to improve our ability to solve machine learning tasks. So again, here we are starting with defining a prompt to the large language model. So, of course, one of the first things to say that if one wants to attempt an AutoML problem as is defined here, or as we understand it here, is that just the task description doesn't suffice. There needs to be more information in the prompt. So what does this enriched context look like? So the enriched context could leverage historical machine learning data. So that means machine learning data of experiments having run on different data sets. So incorporate that within the prompt. And this kind of points to a certain challenge that this resides in heterogeneous formats. So that's like code, configs, logs, and so on. So this means to say that a large language model would work best only if it's normalized, only if this historical machine learning data is canonicalized into a format acceptable to a large language model. So furthermore, a retrieval mechanism is needed. Now we say historical machine learning data, but we all know that large language models are limited by the context length, right? So you can't just feed unlimited amount of context to an LLM. So there needs to be a retrieval mechanism to fetch the relevant parts of this historical data. And finally, deriving a machine learning solution based on historical experience, in essence, is also mathematical thinking and logical reasoning problems. So this points to a wider research area. So in essence, this says that also a reasoning mechanism is needed. So, so within this work of the ML Copilot, that's how the researchers define the problem. So they have two stages within the problem specification. One is the offline stage. The offline stage is almost like an initialization of the historical space of problems that exist. And the online stage is basically where a user comes to a large language model and types in a new task that it wants to solve and says, okay, here's my new problem, and so what should I do, basically. So that's kind of very simplistically put. But to look a little bit more at the offline stage, what happens here in at least the ML Copilot work, or at least how they introduced it. So they kind of source the data from different places, and they expressed it as the task, solution, and the evaluation performance metrics. However, they observed that, the solution came in various formats. A solution could be a program, a solution could be a table, it could be, like a JSON output or something like that. So they needed to implement a canonicalization function that converted this to a standard format. And based on this, an LLM was prompted to kind of create knowledge or infer knowledge over this historical information that was given to the LLM. So that's kind of all the offline stage. So this is instantiation of your space of problems that exist. And the online stage is, of course, where a user comes with a new task to the ML Copilot. So basically, then it has a retrieval function that kind of fetches similar tasks from this whole pool of experiences to the task that the user put into the Copilot, whatever, interface. And it kind of brings it into the context of the prompt that it's building now, step by step. In addition, it also brings in the knowledge that was elicited from the LLM, from the experience. And so this is kind of then prompted to the LLM, so that's step 4. And then the LLM kind of produces, or at least this agentic model with interacting with the LLM produces, the solution. So it's basically saying fine-tune on a pre-trained, so it's suggesting the model to fine-tune on with low learning rate and low weight decay. So they kind of evaluated on 3 research questions, but it's just, I think in essence, what we're all looking for is whether this outperforms traditional approaches or whether it can outperform like simple interactions with LLMs. So is this ML Copilot framework working, right? So at the time, this was work published in, the preprint published in 2023. So they used the GPT 3.5 model. And they had 3 benchmarking data sets. So I believe some of these might be familiar to you as well. So that's like HPOB, PD1, HyperFD. Just quickly, HPOB is like, 100 data sets from OpenML. So it has like a solution space for fixed machine learning algorithms like random forests and so on. PD1 is basically a neural network tuning data set, and it has 24 classification tasks, image classification, next token prediction, and so on. And each task is associated with a predefined neural network. So now we are kind of actually entering the space of neural networks and optimization there. And HyperFD is this neural face detector kind of data set. And it kind of like wants to configure for different parameters around it. And a question here is that these benchmark data sets were used in ML Copilot, yes, but it's also important to think about in terms of like LLM-based AutoML. Like, is the large language model actually reasoning, or has it seen this data before and is just repeating what it's seen? So that's also a factor that researchers often control for. Like what the LLM has seen before, so that it's not like, cheating on the problems and is actually solving for the problems. So that was something that the researchers in this work did control for. So basically the benchmarking data sets that they used had numerous machine learning tasks, broad spectrum of scenarios, and so on. They used the metric at T, which was defined as the best metric performance average among the first T suggested solutions. So this metric is really data set dependent or benchmark dependent. So the kinds of baselines, so this is the results table. So at the bottom, you see the ML Copilot results against the 3 benchmarking data set scenarios, which are the 3 main columns. So we basically see, in this pink highlighted box, which are some of the traditional AutoML or meta-learning methods, as well as LLMs prompted in a 0-shot setting versus LLMs prompted in a few-shot setting. So they kind of actually did quite rigorous experiments in this work. So first of all, they saw on the HPOB dataset that ML Copilot achieved the highest normalized accuracy across 3 trials. And also notably, the few-shot LLM surpassed the traditional baselines. So they're actually seeing some promise of leveraging such kind of like frameworks with like retrieval, reasoning, everything like incorporated. On the PD1 dataset, the ML Copilot surpassed all baselines as well, but the 0-shot and the few-shot didn't work as well. So this offers credence to say that, okay, it's important to know like these retrieval mechanisms or the knowledge selection mechanisms are actually working. And finally on HyperFD, which is this face detection kind of model, ML Copilot didn't quite pass all the baselines, so to speak, but it surpassed most baselines. And the few-shot also achieved comparable performance to many baselines. So final thoughts. This data set is kind of like an exemplary demonstration of a framework that like unleashes the power of large language models to solve, practical machine learning tasks under the AutoML paradigm. So I guess in my talk, we've looked at, some of the notable works that we surveyed in our paper. And all of the works that we looked at focused on an advancement, right? So it's expanding the scope of LLM applications to a broader spectrum of complex problems around the theme of scientific experimentation and AutoML. So that was kind of like the message with all of these benchmarks and so on. So this kind of like ties into like the question in one of my earlier slides was, or in the beginning of this talk, is can we develop an AI agent capable of conducting machine learning experimentation autonomously? And this is kind of like an open question, right? That's up there for all of us to ask. And that's the survey paper. And again, we also look at various other aspects around like science and LLMs in science. And with this, I thank you for your attention, and I would like to acknowledge the BMBF that has funded my project and also much of my work till this point. Thank you very much.